Hi, this is Qiaochu at Lehigh University. Today we're going to talk about the problems in homework 2. Let's take a look at the first problem. A siphon was used to drain the water from the upstream to the downstream. The problem provides us the cross-sectional area. It equals to 12 square feet. The height between the entrance of the siphon to the summit is 15 feet. The height between the upstream water surface to the summit is 8 feet, and the height between the downward reservoir to the summit is 60 feet. The friction head loss it equals to 2.5 times the velocity head, and the distance from the siphon entrance to the summit, we call it L1, is 1/5 the total siphon length. Because the friction factor, diameter, and the velocity along the siphon, they do not change. So based on the Darcy-Weisbach equation, we can know that the friction loss in L1, it equals to 1/5 of the friction loss along the siphon. If we bring the friction loss equation to this one, we can get the friction loss in L1, it equals to 0.5 times the friction head. And we also know the value of the critical pressure. It equals to negative 9.8 pounds per square inch. So if the pressure is less than this value, then there is a danger of cavitation. In this problem, we want to determine the danger of cavitation at the summit point. In other words, this question asks us to calculate the pressure at the summit and then to compare this value with the critical pressure. So to solving this problem, we need to pick 2 points to write down the energy equation. If we choose a point A and a summit point, there is a problem because at the summit point, we only know its height or the elevation. We do not know its pressure and the velocity. So there are 2 unknowns. We cannot solve the 2 unknowns in one equation. So first we choose to write down the energy equation at point A and point B first to calculate the velocity, and then to use another energy equation at point A and S to solve the pressure at the summit. First step is to write down the energy equation at point A and point B. HA plus PA over gamma plus VA squared over 2G equals to HB plus PB over gamma plus VB squared over 2G plus the head loss, which is HL. Because we assume the datum is at a point B, so HB equals to 0. And HA, it equals to H3 minus H2. Because we already know the value for H2 and H3, then we can get HA equals to 52 feet. And because the point A and point B are all on the free surface, so the pressure at this point is equal to atmospheric pressure. And we assume that the velocity at these 2 points is close to 0. And the head loss, it equals to the friction loss plus, because there is a squared edged entrance, so there is an entrance loss, which is HE. And because there is a submerged pipe discharge the water to the reservoir at the downstream, so there is a discharge loss represented by HD. If we bring this 5 equation into the energy equation, we can get the friction loss times the entrance loss times the discharge loss equals to 52 feet. Because the friction head is provided right over there, equals to 2.5 times the velocity head, which is 2.5 times velocity head. Because there is a squared edged entrance, so there is an entrance loss. The coefficient of the entrance loss it equals to 0.5, which can be found in the figure 3.12. And because there is a submerged pipe draining the water into the downstream reservoir, there is a discharge loss. And on page 79, we can find its coefficient equals to 1. So this equation equals to 52 feet. Then we can get the value of the velocity head. It equals to 13 feet. So the next step is to write down the energy equation. At point A and S. So it's HA plus PA over gamma plus VA squared over 2G equals to HS plus PS over gamma plus VS squared over 2G plus the head loss in L1. And because we already know that HA equals to 52 feet, HS equal to H3 equals to 60 feet. The point A is at the surface, so PA is 0 and the velocity at point A is also equals to 0. The velocity at the summit is equals to the velocity along the whole siphon, which is equals to v. So the Vs squared over 2g, it equals to the velocity hat. We already know its value equals to 13 feet. So the head loss in L1, it equals to the entrance loss plus the friction loss in L1. Because we know that the coefficient is 0.5. The friction loss in L1 it's equals to 0.5 times v squared over 2g. It's right over there. So this equation is then we can get a value of the head loss in L1 equals to 13 feet. After we bring this equation, this value into the energy equation, then we can get the pressure at the summit equals to minus 34 times specific weight of water. It equals to minus 34 times 62.3 is the specific weight of water, and there is a unit transformation. So we can get the pressure at the summit equals to minus 14.7 pounds per square inch. So we can compare the pressure at the summit with the critical pressure, and because the pressure at the summit is smaller than the critical pressure, hence the cavitation is a concern. At summit. So this is the result for the problem 1. Let's take a look at problem 2. A pump will be used to lift the water from the aquifer and then transported to the water treatment plant. The flow rate equals to 50 cubic feet per second. A 24-inch pipe is used with an entering screen. The coefficient of the loss caused by the entering screen equals to 2.5. And we assume the friction loss on the suction side of the pump are negligible. The H sub F equals to 0. In this problem, we want to determine the maximum height above the aquifer that the pump can be placed without encountering cavitation. In other words, in this problem, we want to determine the maximum value of H sub B. So to solving this problem, we want to determine the datum, which is at the surface of the aquifer. So we want to write down the energy equation at the point A, which is at the surface of the aquifer, and also the suction side of the pump, which is at the point B. The energy at point A is HA plus PA over gamma plus VA squared over 2G equals to HB plus PB over gamma plus VB squared over 2G plus the head loss. And because the datum is at the surface of the aquifer, then HA equals to 0. And at the point A, we assume the pressure it equals to 0, and the velocity at the surface of the aquifer also equals to 0. Then these three terms can be cancelled. The HB is our unknown, and because the critical pressure head that may cause cavitation, it equals to negative 23 feet. We can find this value on page 99. And the velocity at the point B, it equals to Q over A equals to 4 times Q over pi times D squared. If we bring the value into this equation, we can get the velocity equals to 15.9 feet per second. The head loss is equals to the friction loss. We also call the friction loss as the major loss. And plus, we call other loss as a minor losses. So in this problem, the minor losses contains the loss caused by the entering screen. Because the H sub F equals to 0, and the loss caused by the entrance screen, it equals to the coefficient times the velocity head. After we bring the value of case B and also the velocity at the point B, we can get the head loss is equals to 9.81 feet. After we bring this equation back into the energy equation, we can get the maximum height that we can place our pump, which is HB equals to 9.265 this is the result for this problem. Let's take a look at problem 3. Here is a pump will be used to lift the water from the reservoir A to the reservoir B, and we know the total length of the pipe it equals to 100 meter, and the diameter is 80 centimeter. The flow rate equals to 4.5 cubic meter per second, and the water temperature is 20 degrees Celsius. In this problem, we want to determine the maximum distance from reservoir A that the pump could be installed without encountering the cavitation problems. In other words, in this problem, we want to determine the maximum value of LP to avoid cavitation. To solving this question, we want to write down the energy equation at the point A, which at the water surface in reservoir A, and point B, which represented the location of the pump. So the energy equation at point A is HA plus VA squared over 2G plus PA over gamma equals to HP plus VP squared over 2G plus P over gamma plus the head loss. And because we assume the datum is at the location of the pump, so the HA equals to 4 meter and HP equals to 0. Because the point A is at the water surface, so we assume the VA equals to 0 and also PA equal to 0. And because we can know that from the textbook, the critical pressure head that may cause cavitation, it equals to -7 meter. So the P over gamma equals to 0.7 meter. And we can calculate, because the flow rate and diameter are given, we can also calculate the velocity. At point P, it equals to Q over A equals to 4 times Q over pi times D squared. It equals to 8.95 meter per second. And then we can know that the velocity head, it equals to 4.08 meter. The head loss in this problem, it equals to the friction head loss plus the loss caused by the entrance, because there is a squared entrance. After we substitute substitute this equation back into the energy equation, we can get the friction loss plus the loss caused by the entrance. It equals to 6.92 meter. So our next step is to calculate the value of friction factor and also the loss caused by the entrance. Let's look at the friction loss first. The friction loss is given by Darcy-Weisbach equation. It's friction factor times the LP in our problem, over diameter times Vp squared over 2G. In this equation, the only unknown is LP. So the value of friction factor equals to the relative roughness and the Reynolds number. Because it is a rough concrete pipe, we can search the value of the roughness on page 66. The roughness, it equals to 0.6. Then we can calculate the relative roughness. It equals to 0.00075. And because the water temperature is 20 degrees Celsius, then the kinematic viscosity, it equals to 10 to the power of -6. Then we can calculate the Reynolds number. It's velocity at the point P times diameter over the kinematic viscosity. It equals to 7.16 times 10 to the power of 6. After we know the relative roughness and also the Reynolds number, we can search the friction factor on Modi diagram. The friction factor, it equals to 0.0185. Then we can use the value to represent the friction factor. It equals to 0.0185 times our unknown LP over 0.8 times 4.08. The HF, it equals to 0.094 times L sub P. And then we want to calculate the loss caused by the entrance. it equals to the coefficient times the velocity hat. Because it's a squared entrance, according to the figure on page 77, we can know that the coefficient equals to 0.5. And we already know the value of the friction hat, it equals to 4.08 meter. So the loss caused by the entrance is equals to 0.5 times 4.08 equals to 2.04 meter. So currently we can bring the value of the loss of entrance and also the friction loss back into this equation. So we will get zero 0.094 times L sub P plus 2.04. It equals to 6.92. After resolving this equation, we can get L sub P, it equals to 51.91 meter, which is our result for the problem 3. For problem 4, there is a pipeline system was being used to transport the water from the reservoir A to the reservoir B. The problem gave us information about the total length of the pipe. It equals to 40 meter. And it also provides us the length for each section of the pipe. And the diameter of the pipe is 4 inch. The water temperature is 20 degrees Celsius. And based on the water temperature, we can determine the specific weight of water and the kinematic viscosity. The head loss in the pipeline system contains 2 parts. The first one is the major loss, which is also called the friction loss. The other part is the minor losses. The minor losses in this problem contains 4 parts. The first one is the squared entrance. The second one is the discharge. And the third and the fourth come from 2 valves. We can find those coefficients on the textbook. Because the pipe are made by the commercial steel, so on the textbook we can find the roughness. It equals to 0.045 millimeter. And then we can calculate the relative roughness. And we can use the relative roughness when we need to determine the friction factor. Because this question asks us to determine the minimum pressure P0 that would keep the pressure head throughout the pipe positive. To solve this problem, first we need to determine the location that has a minimum pressure and set the pressure at the point it's equals to 0. And to determine the location that has a minimum pressure, let's take a look at the energy equation right at the point A at the random point. On the left-hand side is energy at the point A, which is a constant. On the right-hand side is the energy at a random point along the pipeline. Because the flow rate and the diameter along the pipe, they do not change, so the velocity hat here is a constant. Therefore, if the point has a higher value in height and the head loss, they will have a smaller value in the pressure head. So let's look at a figure. The point has a highest height is at a 0.4 and 0.5, and because the 0.5 is further from the point A, which means that they may have larger value in the friction loss. So we can determine the location has a minimum pressure is at a 0.5. We want to set the pressure at the 0.5 equals to 0. And then we want to write down the energy equation at a point A and 0.5. The height at point A is given, which equals to 10 meter. The height at point 5 it equals to 9.5 meter. Because the point A is at the water surface, so the pressure at point A it equals to P sub 0. And we set the pressure at point 5 it equals to 0. The velocity at point A it also equals to 0. And the velocity at the point 5 it equals to the velocity in the pipeline. The head loss from point A to the point 5 it equals to the friction loss from A to 5 plus 2 minor loss, which is the loss caused by the entrance and the first valve. Because the friction loss is given by the Darcy-Weisbach equation, which is friction factor times the length from point A to point 5 over diameter times V squared over 2G. The minor loss it equals to their coefficient, which is represented here. Times V squared over 2G. If we substitute this parameter back into the energy equation, then we can get P sub 0 it equals to 1 plus friction factor times 32.5 over 0.102 plus 0.5 plus 12 times velocity square over 2g minus 0.5. After we simplify this equation, we can get the pressure head equals to 13.5 plus 318.63 times the friction factor times velocity head minus 0.5. So in this equation, we have three unknowns. The first one is the pressure sub-zero, and the velocity, also the friction factor. Because the P0 is the parameter that we need to calculate in our problem. So let's take a look at the friction factor. The friction factor, it is related to the relative roughness and the Reynolds number. Because the Reynolds number equals to the velocity times diameter over kinematic viscosity. The velocity is unknown. So currently we only know the value of the relative roughness. So we cannot use Moody diagram to determine the friction factor. Therefore, we need to make an assumption. So we need to assume the friction factor equals to 0.02. And then we will need to test our assumption later. So currently we can bring our friction factor back into our equation. We can get the pressure head, it equals to 19.9 times velocity square over 2g minus 0.5. We call it equation 1. Now we can see in equation 1 we still have two unknowns. Therefore, we need to pick another 2 points to write down the energy equation. Then we can bring those equations together to solve the two unknowns. So the third step is to write down the energy equation at point A and point B. M plus pressure point A over specific weight of water equals to height at point B plus the velocity square over 2g plus the pressure at point B plus the head loss from point A to point B. The height at point A, it equals to 10 meter. The height at point B, it equals to 7.5 meter. Because the point A and point B are all at the water surface, so the velocity at these 2 points equal to 0. Then, because the pressure at the point B, it equals to atmospheric pressure, and we use relative pressure, so the P sub B equal to 0. The head loss from point A to point B equals to the friction loss from these 2 points, along these 2 points, plus the minor losses, which are the entrance plus the discharge, and loss caused by the 2 valves. The friction factor, the friction loss, it's given by the Darcy-Weisbach equation, which is the length over diameter times square over 2g. The total minus losses equals to their coefficient. These values are all given here, and times velocity square over 2g. After we bring this value back into the energy equation, we can get P0 over gamma equals to 415 times friction factor plus 0.5 plus 12 plus 10 plus 1 times velocity square over 2g minus 2.5 meter. And then after we bring the friction factor based on our assumption, which is equals to 0.02, then we can get P0 over gamma equals to 31.3 times velocity square over 2g minus 2.5. We call it equation 2. If we bring the equation 1 and the equation 2 here, we have 2 unknowns and 2 equations, so we can solve the velocity. It equals to 1.86 meter per second. Then we can test our assumption by calculate the Reynolds number. It equals to velocity times diameter over kinematic viscosity. It equals to 1.9 times 10 to the power of 5. And because the relative roughness is given over there, equals to 0.000441. Then we can get the friction factor by reading the Moody diagram. We can have a new friction factor equals to 0.08185. Because the friction factor we just calculated is different with our assumption, so we need to use the calculated friction factor as our new friction factor and bring this value back to this equation to update our equation 1, and then bring this value back to this equation to update our equation 2. So after we bring this value back into these two equations, we will get the updated equation as when the friction factor it equals to 0.0185. The equation 1 is P0 over gamma equals to 19.4 times velocity hat minus 0.5. This is our new equation 1, and our new equation 2, it equals to 30.8 times velocity over 2g minus 2.5 is our new equation 2. Two unknowns and two equations. Then we can get the velocity it equals to 1.86, which is similar to our previously calculated velocity. So we can make the conclusion that the friction it equals to friction factor equals to 0.0185. We need to bring the velocity back to either equation 1 or equation 2 to calculate the value of P sub 0. It equals to 19.4 times 1.86 squared over 2g minus 0.5, and then times specific weight of water, which is given here, is 9,790. So after the calculation, we can get P sub 0. It equals to 28.6 kilopascal. So this is the result for our problem 4. The problem 5 is a 3 reservoir problem. It provides us the information about the elevation of the water surface. And it also provides us the length and the diameter of each pipe. The roughness of the pipe is also given, so we can calculate the relative roughness of each pipe. Because the water temperature is 68 Fahrenheit, therefore we can determine the kinematic viscosity. And the pressure head at the junction is also given, which is 30 feet. In this problem, we want to calculate the flow rate in each pipe and the elevation at the junction J. If we want to solve this problem by hand, so we need to follow the steps provided on the slides, lecture 4, page 5 to 8. So the first step is to assume the total energy at junction J. It equals to 5,170 feet. So the total energy at junction J, it is the same as the reservoir 2. So the flow rate in pipe 2, it equals to 0. Then the next step is to calculate Q1. By using Darcy-Weisbach equation. The friction loss equals to the elevation at the water surface of the elevation of the water surface in reservoir 1 minus the elevation of the water surface at reservoir 2. It equals to friction factor times the length over diameter times V squared over 2G. Then we need to bring the value into those parameters. We can have it equals to friction factor times the length is 4,000. The diameter is 3 times velocity over 2 times 32.2. We call it our equation 1. We can see that the friction factor, the Reynolds number, are all unknowns. And we only know the relative roughness. It equals to 0.00013. Then we need to make assumption. We assume the friction factor in pipeline 1, it equals to 0.0127. After we get the value of the friction factor, we can bring this value back to the equation 1 to solve the velocity. We can get the velocity, it equals to 10.68 feet per second. After we get the velocity, we can calculate the Reynolds number. Is velocity times diameter over kinematic viscosity. It equals to 10.68 times the diameter is 3 feet. So over 1.08 times 10 to the power of 5. It equals to 2.97 times 10 to the power of 6. We call the equation to calculate Reynolds number as equation 2. So right now we have the value of Reynolds number and the friction and also the relative roughness. So we can use the Moody diagram to determine the new friction factor, which is the new friction factor. It equals to 0.0132. Because this value is different with our assumption, so we need to use the new friction factor and bring it back to equation 1 and 2 to update the velocity and the Reynolds number. we can get the new velocity equals to 10.47 feet per second. The Reynolds number, it equals to 2.9 10 to the power of 6. And because we have the relative roughness and the Reynolds number, then according to Moody, we can get another friction factor. It equals to 0.0. Because our friction factor in pipeline converts to a stable value, we can make a conclusion that the friction factor it equals to 0.0132. Then we can use the velocity here to calculate the flow rate. The flow rate in pipeline 1, it equals to the velocity times cross-sectional area. It equals to velocity times 1/4 times pi times d1 square. Q1, it equals to 74 cubic feet per second. The step 3. The step 3 is to calculate Q3 by using Darcy-Weisbach equation. The friction loss in pipe 3, it equals to the difference of the elevation of the water surface equals to the friction factor times the length over diameter times the velocity square over 2g. We call it equation 3. Because the friction factor and the Reynolds number are all unknowns, and based on the relative roughness, it equals to 0.0001. We assume the friction factor in pipeline 3, it equals to 0.012. If we bring the F3 back to equation 3, we can calculate the velocity in pipeline 3. It equals to 22.38 feet per second. And then we can calculate the Reynolds number. Velocity times diameter over kinematic viscosity. The Reynolds number, it equals to 8.3 times 10 to the power of 6. And because we know the Reynolds number and the relative roughness, according to the Moody diagram, we can get the friction factor. It equals to 0.0123. Because it's different with our previous friction factor, then we need to bring this value back to the equation 3 and equation 4 to update the velocity and the Reynolds number. We can get the velocity, new velocity, equals to 22 feet per second. And the Reynolds number, it equals to 8.2 times 10 to the power of 6. And then we can read a new friction factor. In Moody diagram. It equals to 0.0123. Then we can say that the friction factor converges to a stable value. And we can use the velocity here to calculate the flow rate in pipeline 3 equals to the velocity times the area. It equals to the velocity times 1/4 times pi times d squared. The flow rate in pipeline 3, it equals to 278 cubic feet per second. Then the step 4 is to check the continuity equation at the joint point. So we need to check. To see if it is equal to 0. Sigma q at joint point, it equals to q1 plus q2 plus q3. And because the q1 here is an inflow, so it's positive. It is 74 cubic feet per second. Q2 is 0, and Q3 its direction is from the joint point to the reservoir 3, so it's an outflow, so it should be negative. Then it's minus 278 cubic feet per second. Because it equals to negative 204 cubic feet per second. Because a sigma q, it equals to a negative value, it doesn't equal to 0. Therefore, we need to make another assumption of the total head at point J, and then repeat step 2, 3, and 4 until it equals to 0. To achieve that, we want to increase the value of Q1 and decrease the value of Q3. Therefore, we need to assume a smaller total head at joint J. So after few trials, which means that repeat step 1 to 4, we can get the total head at point J, it equals to 5,163.5. And meanwhile, we can get the velocity in pipeline 1, it equals to 11.57 feet per second. The velocity in pipeline 2, it equals to 9.33 feet per second. And velocity in pipeline 3 is 21.08 feet per second. And its corresponding friction factor is 0.0132. 0.012, and friction factor in pipeline 3, it equals to 0.0123. Then we can calculate the flow rate in each pipeline. It equals to velocity times the area, it equals to 82 cubic feet per second. Q2, it equals to 183 cubic feet per second. And Q3, it equals to 265 cubic feet per second. And total flow rate at the joint point, it equals to Q1 plus Q2 plus Q3. It equals to 82 plus the 183 minus 285, which is equals to 0. Satisfy the continuity equation. So the flow rate in the pipe is in this direction from the reservoir 2 to the junction. And then we can calculate the elevation at the junction. The total energy at the junction J, it equals to elevation plus the pressure head. It equals to, we already know here is 5,163.5 feet. And because the pressure head is given equals to 30 feet. Therefore, the H, the elevation at the junction J, it equals to the total energy minus the pressure head equals to 5,100.5 minus 30. Then the elevation at junction J, it equals to 5,133.5. So this is a result for the problem 5. The problem 6 is also a 3 reservoir problem. In the problem 6, it provides us information about the elevation of the water surface in reservoir 2 and 3. We know the length and diameter of the pipe, and it also provides us the roughness. Then we can calculate the relative roughness in each pipe. And we know the elevation at the joint point J, it equals to 2,049 meters. And we also know the pressure at this point. And because the specific weight of water, we can find it on the textbook, then we can calculate the pressure head at point J, it equals to 10 meters. In this problem, we want to solve the elevation of the water surface in reservoir 1. To solve this problem, first, let's write down the total energy equation at the point J. Hj equals to is elevation plus the pressure head plus the velocity head. The elevation at point J is given. It equals to 2049 meter. The pressure head, we calculate here, it equals to 10 meter. We assume the velocity, it equals to 0. Then we can get the total energy at point J, it equals to 2059 meter. So the next step, let's take a look at point J and reservoir 2. Because the reservoir elevation of the water surface in reservoir 2 is 2090, it is larger than the total energy at point J. Hence, the flow is moved from the reservoir 2 to the joint point. We choose one point at the water surface in reservoir 2 to write down the energy equation. Then we can get H2 plus V2 squared over 2G plus P2 over gamma equals to plus the head loss. The H2 is given, it equals to 2090 meter. We assume that because this point 2 is at the water surface, so the velocity and the pressure at point 2 are all equal to 0. And if we bring the value of the total energy into this equation, we can get Hgj plus Vj squared over 2j plus Pj over gamma. It equals to 2059 meter. If we bring this this value back into the equation, we can get the head loss. It equals to 2090 minus 2059. And this value, it also equals to the Darcy-Weisbach equation, which is given by friction factor times is L2 over D2 times the velocity in pipeline 2 over 2G. To determine the friction factor, we know the relative roughness in pipe 2, it equals to 0.0015. And because in this problem it told us we assume the flow in the pipe is a complete turbulence. Then, according to the Moody diagram, we can get the friction factor. It's close to 0.022. And then if we bring this value back to the Darcy-Weisbach equation, we can get the velocity. The velocity in pipeline 2, it equals to 3.04 meter per second. Then we can calculate the flow rate. In point 2, it equals to the velocity times cross-sectional area. It equals to 0.382 cubic meter per second. Then let's take a look at point J and the reservoir 3. Because the elevation of the water surface in reservoir 3 is smaller than the total energy at point J. Then the water is flow from point J to the reservoir 3. Now let's write down the energy equation for the point at the joint point J and the point at the water surface in the reservoir 3. H3 plus P3 over gamma plus V3 squared over 2G. Because the flow is from the joint point to the reservoir 3, so we need to add head loss to the total energy at point 3. And then the energy at point J, it equals to the elevation at the point 3 of the point 3, it's given. It equals to 2020 meter. Because the point 3 is at the water surface, the pressure and its velocity are all equal to 0. and total energy at point J is given here. It equals to 2059 meter. The head loss from the joint point to the reservoir 3 contributed by the friction loss, which is given by the Darcy-Weisbach equation, is friction factor times the length over diameter times the velocity in the pipe over 2g. After we bring this value back into the energy equation, we can get the head loss equals to 39 meter. In this question, we have two unknown, and for calculating, determining the friction factor, we already know the relative roughness. It equals to 0.0012. Because we assume it is a complete turbulence. According to the Moody diagram, we can get the friction factor. It's close to 0.021. Then if we bring the friction factor back into the Darcy-Weisbach equation, we can get the value of the velocity in pipeline 3. It equals to 2.76 meter per second. Then based on the equation, velocity equals to flow rate equals to velocity times area. We can get a velocity in pipeline 3. It equals to 0.542 cubic meter per second. The sigma q at joint point J, it equals to 0. Then Q1 plus Q2 plus Q3 is 0. Q1 is unknown. Q2 equals to 0.382 because it is flow from the reservoir 2 to the junction, so it's a positive. And Q3 is from the junction to reservoir 3, so for the junction J, it's an outflow. It should be negative, so it's negative 0.542. equals to 0. Then we can get the value of the flow rate in pipeline 1. It equals to 0.16 cubic meter per second. Then we can calculate the velocity in pipeline 1. It equals to the flow rate over the cross-sectional area is 2.26 meter per second. Okay, currently we have the velocity in pipeline. It equals to 2.26 meter per second. And this problem asks us to calculate the value of the water elevation of the water surface in reservoir 1. And because this term can be found in the energy equation, so the next step is to write down the energy equation in point 1 and joint point J. The point 1 is at the water surface. Because the flow we just calculated is a positive value, so we can find the flow is water is flow from the reservoir 1 to the joint point J, and then we should add a loss head term on the right hand side. H1 is our unknown, and because the point A is at the free surface, so the pressure and the velocity are equal to 0. And because the total energy at the joint J we just calculated, it equals to 2059 meter. And the head loss from the reservoir 1 to joint point, it equals to the friction loss is given by the Darcy-Weisbach equation. It's the friction factor times the length over diameter times V1 square over 2G. If we bring this equation back into the energy equation, we can get the H1, it equals to 2059 plus the friction factor times L1, it's 1900 over diameter equals to 0.3. Times V1 square over 2G. Let's take a look at friction factor 1, because the relative roughness is given equal to 0.002, and the Reynolds number is the velocity times diameter over kinematic viscosity, it equals to 2.26 times 0.3 over 10 to the power of minus 6. It equals to 6.78 times 10 to the power of 5. After we got those two information, we can find the friction factor in Moody diagram. The friction factor equals to 0.0235. After we get the value of the friction factor, we can bring the friction factor and the velocity back to this equation. We can get the H1 equals to 2059 plus 0.0235 times 1900 over 0.3 times 2.26 square over 2 times 9.81. Then we can get the elevation of the water surface. It equals to 2097.7 meter. So this is our final result for the problem 6.